Hello everyone and welcome to lecture 10. Today we will get started with looking at constraints in an optimization setting. So far we have been looking at optimizing a single function without any constraints. When you add constraints, which is normally the case in many practical applications, the algorithms and the theory become a little bit more complicated. The methods and the software also become a bit more tricky to implement, and we get a lot of interesting cases in how we can transform these models into something more tractable from a computational point of view. So this is a very interesting part of the course, and we will spending the remaining 2/3 of the course on problems with constraints. The recommended reading for this lecture is chapter 7 from our textbook by Roger Fletcher, and also some introduction part of chapter 8 on linear programming. A nonlinear problem with constraints can be written generally as the problem of minimizing a given function f of x over all possible x, and we are talking about vectors of variables. So x is in dimension of n real variables. In addition to this objective function, we also have one or more constraints which can be some nonlinear relation which is constrained to take only certain values, and we can also have a few constraints where we don't have equality relation or an equality constraint, but rather an inequality constraint. I can have a bunch of these. So obviously these are called equality constraints. And the constraints with an inequality sign are obviously called inequality constraints. We will assume for rest of the course that K and L are finite. They can be 0. Notice that we have only greater than equal to sign in our inequality constraints, but that is not a real restriction. You can also have less than equal to type of constraints, but not we are not allowed to have strict inequalities. We will discuss it towards the end of this lecture. So now when you have constraints, then certain x's will not be allowed by these constraints. So we need a little bit more terminology. So we say a point x bar is feasible to the problem if it satisfies all the constraints. Given a point x bar in Rn, it is usually quite easy to check whether it is feasible or not. All you have to do is put the value of x in all these expressions of constraints and see whether they are satisfied or not. If it satisfies all the constraints, then we say that it is feasible. The set of points, the set of all feasible points is called the feasible region. Usually denoted by R. Let's consider an example. Minimize a quadratic function, let's say x1 square plus x2 square. So here x is in a two-dimensional Euclidean space subject to 2x1 minus x2 plus 1 equal to 0, and that's it. So in this case we have k is 1 and L is 0. We don't have any inequality constraints, and we have exactly one linear constraint, because this function is affine in the variables. So let's look at some points. So if I ignore the constraints totally, then the point x 0 0 is the obvious optimal solution if I just want to minimize the objective function without any constraints. However, does this point, let's say x1, does not satisfy constraints, Okay, so we say x1 is not a feasible point. Another point, let's say three 7 is feasible because it is satisfying all constraints. Let's try to draw the feasible region and some contours of the objective functions to just get an idea of what we are trying to do. So so 0, 0 is where my objective function takes the minimum value, but that is not a feasible point. These are the contours of my objective function. These are concentric circles. If I look at the constraint and try to draw all points which satisfy these constraints, I will get so minus half 0 actually lies on this constraint, and so does 1 comma 0. If I draw a straight line passing through these 2 points, so my feasible region is actually all points on this green line. Okay, and as I move along this line, my objective function will keep changing, and I would like to find a point which has the minimum value of x1 square plus x2 square in this region R. So it's not too difficult to see that the point minus 2 by 5, 1 by 5 is optimal for this problem. So and this can be viewed geometrically. If I keep growing these concentric circles, then I will hit my feasible region first at this point. And the value at this point is actually 1 by 5, I think. It's easy to see that this point is feasible. I can just put these numbers in my constraint and check whether it satisfies this constraint or not. It's not very straightforward to see why this point is optimal mathematically. Geometrically, we can probably see that this point is optimal. But with a little bit of thought, what you can try doing is substitute x1 from this constraint into the objective function, and try to get an unconstrained problem. So I can rewrite the problem as x1 square plus 2x1 plus 1 whole square, and now I have only one variable left. X2 is uniquely determined once x1 is fixed. Since x2 does not appear in the objective function, I can even ignore it. Once I find the minimum of this function, I can plug the value of x1 and get x2. So at least for this problem, there is a way around by substituting some variables out and solving an unconstrained problem to find the minimum point. Okay, let's add some more constraints to this problem to make it a little bit more interesting. So again, my objective function is still the same, quadratic in x1 and x2. I'm still in 2 dimensions. I still have the same constraint I had earlier. Let's add some bound constraints now. So in addition to this equality constraint, let me add x1 greater than equal to 1 and x2 less than equal to 3. Notice that here we are introducing a less than equal to sign, even though our earlier definition of the nonlinear problem said that all inequality constraints must have greater than equal to sign only. But as we will see shortly, this doesn't change the problem significantly, and it's very easy to get back the problem in the form we want. So now, in addition to just this green line, I am also restricting x1 to be more than 1. So that means we are saying that x1 should be to the right side of x1 equal to 1. So all points on this blue line denote x1 equal to 1. So by adding this constraint, we are saying that we have to be on the right of this constraint only. So my previous point minus 2 by 5 comma 1 by 5 is no longer feasible to my new set of constraints. Okay, so so minus 2 by 5, 1 by 5 is not feasible. I have one more constraint, which is x2 less than 3. So that constraint might look like a horizontal line. So this picture is not to scale, so it may appear that there are no points which satisfy all constraints, namely the blue constraints as well as the green constraint, but it is possible that it is still feasible, and my drawing is poor. So let's see if we can find a feasible point. So for example, if I put x1 equal to 1, so 1 comma 3 is a feasible point. Okay, so if I had drawn the picture little bit more accurately, I would have seen a feasible point. Okay, and the function value is at this point is 10, and it's not very clear whether this point is optimal or not. So we will in later chapters try to have some methods or systematic way of saying whether a given point is optimal or not. But at the moment, we are more interested in understanding some of the basic things about constraints and how they affect the solution.